Thank you, Amir. All right, so I'm Michael Forbes. I'm going to talk about polynomial identity testing. So there are going to be a couple lectures on this. What I want to do for this 50 minutes, hopefully, is define the problem and sort of give you a like an idea of what this problem is about, and kind of give you the feel and gestalt and the language of this problem, because we talked about lower bounds and sort of general, complexity classes and so on. But this requires its own taste. Give you some basic lemmas in this area, and then handwave a lot about this hardness versus randomness paradigm, which I'll hopefully explain. Okay, so what is this polynomial identity testing problem? Ultimately, it's the following question. So I'm going to say PIT a lot. That's the acronym for polynomial identity testing, in case that's not clear. Okay, so the question is as follows. You're given a polynomial. Okay, so it's going to be polynomial f of x, and you want to know is it 0? Okay, and so this is a problem. This is an algorithmic question. I'm giving you a polynomial. That's your input, and you're just you have to decide whether it's 0 or not. And this has a lot of algorithmic applications outside of algebraic complexity theory, because oftentimes you can take say even a combinatorial problem and encode it into this sort of question, solve this question, and you get an algorithm for your combinatorial problem. Okay, I mean obviously the difficulty with this question is that in some sense it's very subtle, because you can sort of analyze every word in the sentence and ask what does that really mean? What is the definition of is, it, a, and so on. More interestingly, you can talk about, say, what is f? Here will be n-variate, and it'll be degree d, degree at most d. And so I'm going to sort of stick with these parameters, and at all points, all my polynomials will be n-variate. All of them will have degree at most d. Okay, you know what a polynomial is. What does it mean to be 0? Well, that's a bit of a subtle question. So if you take a polynomial, right, you can expand it in terms of its coefficients. So I write my coefficients in the following way. So there's going to be some field, okay, and I'm going to denote it like this. Alpha sub a is a coefficient. It's going to come from your field. Okay, this thing here, x is going to be a variable, so I write like my vectors with a bar on top. Okay, so x is a vector of variables. There are going to be n of them, and then you have an exponent here. And what this means is you just basically take xi to the ai and you product over I from 1 to n. Okay, so this is a monomial. Then you have some coefficient, based on this exponent vector that comes from your field. So this is a polynomial. And when I'm saying a polynomial is 0, it means that all alpha sub a's are equal to 0. So it's 0 in a very, very strong sense, right? So this is not, for example, so if you take x squared minus x, this is not 0 even over f2. So when I'm saying, something is non-zero, it's non-zero syntactically as an object, as a polynomial, not as necessarily a function. But it's important to note that you can, in all of algebraic computation, we're computing polynomials as polynomials. We're not computing them as functions. But there is important to remember that every polynomial defines a function, and we'll sort of use that later in this talk. Okay, so that's polynomial that's f and 0 and so on. What does it mean to be given? Am I giving it to you for your birthday, via email? I don't know. But the way I'm giving it to you is via an algebraic circuit. Okay, so we defined various notions of algebraic circuits in the morning and yesterday, and that's sort of the input format. Okay, and what makes this problem specifically very challenging is that an algebraic circuit is a very succinct way to encode a polynomial. Okay, because the polynomial is in some sense a large object, but you could have a very small algebraic circuit encoding that. And so let's see a lemma which sort of encapsulates this issue of succinctness. Okay, so this is sort of the first thing, is that PIT is solvable. What's the sort of most naive thing? It's going to be in polynomial in n plus d, choose d time. And this is going to be deterministically solvable. Okay, so I'm going to distinguish between randomized and deterministic algorithms in this talk. And why is it solvable in this amount of time? Well, this polynomial is n-variate and it's of degree d. Okay, and I'm giving you a circuit. What is sort of the brute force expansion of this polynomial? Well, this number is the number of monomials possible in this thing. So basically what's going to happen is you take your circuit, and every time you do multiplication or an addition, you just expand everything into the dense representation, into just a sum of monomials. The number of monomials is this many, so I mean really this is polynomial in this and s, but basically s should always be at most this bound anyways. Okay, so this is sort of the most naive thing you can do. Okay, but the problem is that this is a very big number, whereas s itself could be much smaller. So really what we want to do is we want to do something much better than this naive thing. Okay, so the main question is to get algorithms that are better than this. And the key lemma that sort of powers this whole thing is the so-called Schwartz-Zippel lemma, which is the following. Okay, so suppose that you have a polynomial. Let's assume it's non-zero. Okay, so non-zero, some of its coefficients are non-zero. What we're going to do is we're going to take a subset S of our field. Then I'm going to make a probabilistic statement. Okay, so what is a probability space? Well, this is an n-variate polynomial, following my convention. You take a vector, and it's going to be uniformly chosen at random from the set where all of its coordinates come from S. Okay, so S is going to be a finite set, and this is a finite space. You just choose a point from the space at random. And then you evaluate your polynomial f at this point alpha. The probability that it's 0 is at most d divided by the size of S. Okay, and so this is a pretty basic lemma. I'm going to prove it for you anyways. I apologize if you've seen it 10 or more times. Okay, but I want to prove it to you since it's sort of basic here and important. Okay, so what is the proof? Well, it's going to be induction on n. There are like various proofs, but let's just look at n equals 1. When you have n equals 1, this is a univariate polynomial. Okay, and the fundamental fact about univariate polynomials, if its degree at most d, which again, that's the convention here, right, then it can have at most d roots. Right? There are most d points where it's 0, and I'm choosing uniformly at random, a point from S. So this is sort of immediate. Okay, this is sort of a check mark there. Right? What happens if we have n greater than 1? Well, we're going to do sort of the obvious thing. We're basically going to reduce to the n equals 1 case in some way. Right? So I'm just going to relabel my variables. Hopefully the notation is clear. So I'm going to distinguish one variable y and call all the other variables x. And we can write it as follows. Right? We have f sub I of x. So, and I goes from, say, 0 to d. Okay, so I'm sort of thinking of this as an element of f of x of y. So I'm sort of thinking this as a univariate in y, where my coefficients are polynomials in x. Okay, and clearly, f is at most degree d, so there's at most d things here. Right, but one of the immediate things that you notice about this is that what can we say about the degree of the fi's? Right? Well, the degree of y to the I is I, and the total degree is at most d, so it says that the degree of the fi's is at most d minus I. Okay, so that's something not too hard. All right, so now we want to do what we're supposed to do. Consider this statement that you take a random alpha to place in with x, random beta to place in with y. What's the probability that it's 0? Well, we're going to condition on two possible events, or one event and condition two ways. Okay, so we want to say what's the probability of 0? Well, this is some polynomial, right? It's a degree at most d in y, and let's say it actually depends on y in some way. So the point is that there's going to be some d, which is less than d, such that f sub big D of x is non-zero. Okay, and for all, let's say I bigger than d, f sub d, f sub I is 0. Okay, so basically looking at the maximal degree term in terms of y and looking at that coefficient as something of x. We want to know, look at that coefficient, what's the probability that it's 0, or what's the event that it's 0? So we have f sub d of alpha is 0. We're going to condition on this event. So it could be that this coefficient is 0, and let's condition on that event and use Bayes' rule or whatever. And then there's the other way, where this leading coefficient is non-zero times the probability that that thing is non-zero. Okay, so now we have like 4 terms here, and we're going to do 2 stupid things and 2 smart things. Okay, and I'm never smart enough to remember which is which, but I have my notes. Okay, so let's look at this first term. Let's do the stupid thing. This is some probability, so it's at most 1. Okay, again, my notes come to the rescue. This thing here is also at most 1. Okay, where's the word? Oh, yeah. Okay, so now we have some smart things to do. Let's look at this term here. Right, what's the probability this polynomial is 0? Well, we're going to use our inductive claim here. Right, this is a polynomial on n minus 1 variables, which we've already sort of established. And the degree here, we have this thing. So the degree here should be little d minus big D. So this quantity is at most little d minus big D over S. Okay. Now, that's some smart thing. Now consider this thing. Well, we have that f is a bunch of coefficients plus this leading term. to the d here. But there's nothing else, right? So what I'm assuming here is that this coefficient is not 0. So if we look at this polynomial just in terms of y, where we fix alpha, then this is a univariate of degree d, right? So how many y's could possibly make this expression, how many betas could possibly make this expression d? 0, it's at most d, because there's most d roots, right? So this thing here is at most big D minus over size of s, okay? And then if you add these, this is 1, this is 1, and this is 1, so they don't do anything as it's multiplication. You add these two quantities, and you get exactly what you want, okay? So this is, technical and so on, but you have to see it at least once. Okay, so this is a probabilistic statement, but I want to make a non-probabilistic statement, which is a simple corollary. And it seems stupid, but we'll make it smart later in the talk. Okay, so suppose that you have a polynomial which is non-zero, right? This is a sort of syntactic question about the coefficients. I want to make now this into a functional question. So this polynomial is non-zero if and only if it's non-zero on this set. So here again we're going to have that, say the S, we're going to choose some subset of our field S. We're going to assume it's strictly bigger than D. D is our degree of our polynomial. And what is this here, the statement here? This is basically all the evaluations f on alpha, where you take alpha in your set S to the n. Okay, so this is some discrete set. You evaluate your polynomial on all these things. And this is saying your polynomial is non-zero if and only if one of the evaluations is non-zero, right? And how do you prove this? Well, if it is 0, clearly all the evaluations are 0. If it's non-zero, the probability that it's 0 is strictly less than 1, right? So there must be some point where it's non-zero, and this establishes the claim. Okay, so this is sort of something stupid, but I'll come back to this later. Okay, but what's the main corollary of the Schwartz-Zippel lemma? Well, what's the whole question I'm asking? I'm giving you a polynomial as an algebraic circuit. You want to know whether it's 0 or not. The corollary is that if you evaluate the circuit at a random point, and it's a non-zero polynomial, you get a non-zero evaluation with high probability. So what this gives you is an efficient randomized algorithm for PIT. Is that what I want to say? Yes. Say for general size S circuits. Okay, so in this talk I'm going to make some distinctions between general circuits and restricted circuits like multilinear formulas or depth repowering like Ram Prasad talked in the morning. But basically it's saying that for general size S circuits, you can do randomized PIT. It's efficient, works with very, very high probability. You just basically, you take your circuit and all you need to do is evaluate it. Okay, so you take the syntactic object, you convert it to a function, and you get something, you get this algorithmic question. But there's sort of a catch, okay? And hopefully some of you have caught the catch, which is that this thing works only if the field is large enough, right? Only if I have enough points to actually choose a large enough set, right? So this is true if your field is, say, strictly bigger than like twice D, right? Because then you want this probability to be at most half, and then you can like repeat it as much as you want, okay? So that sort of seems annoying, and it is annoying. So what's the remark here? Is that suppose that you have a small field, okay, something like F2, right? You can't purely talk about is there a non-zero evaluation over the binary field, because that's NP-hard, that's like solving SAT or something. But what you can do, you can still ask this syntactic question, is there a non-zero coefficient somewhere? And basically what you can do is you can simulate a large field, okay? So in some sense, you pretend you're a small field. You think in your head, I really wish I could grow up and be a large field. And you run this algorithm, and it basically works. Okay. But the exercise here to make this all sort of work is how do you actually simulate a large field? Is that you can construct, say, f sub q to the L. So suppose that you have f sub q. F sub q is your field that you're working over. You want to work with a larger field. Okay. You can construct this larger field from the smaller field in time polynomial in q to the L. Okay, there's much more efficient algorithms out there, but this isn't, if you do some basic field theory, this is not too hard to show. Okay, that you can construct this field. And the point is that q to the L only needs to be about 2D. So this is about 2D, so this is a polynomial time construction. Okay, so basically you get your extension field, you run Schwartz-Zippel, and so that basically says, well, we really don't actually need this restriction. We can just simulate the large field and we're done. But for the rest of the talk, I'm going to work in a large field because it's painful otherwise. Okay, but what is, one thing to note is what is the computational model? Because, to some extent, a lot of computer science, we're working over Turing machines, working with bits and so on. But here we have fields, right? Does this question make sense over complex numbers? Does it make sense over weird fields that you could never even dream of? So to make this sort of a nice abstraction, what I'm going to do is I'm only going to count field operations. So I'm not going to look at, say, bit complexity. Typically, any algorithm that you basically would design would actually have good bit complexity. But basically what we're doing is we're going to work over some sort of abstract field where you're allowed to do things like addition and multiplication and division and zero testing all for free. And you're just basically going to count the number of field operations. That's sort of the model that's convenient to work in. It's a nice abstraction. Okay. Okay, so that's a computational model. And now I want to make this is like a series of remarks. Some more remarks. So the question is, how much do I actually need to see this circuit? Right? I'm given this circuit, but how am I really given it? And so there's two models I want to talk about. There's something called the black box model. Black box. So what is the black box model? Well, it's inspired by the Schwartz-Zippel lemma, right? You're given a circuit, and you want to know, is it 0 or not? All you're doing using Schwartz-Zippel is you're just evaluating at a random point. So even though I'm giving you a circuit, you're not actually probing the circuit structure in any way. All you're doing is using the circuit structure to evaluate that polynomial. And so you basically could be given the polynomial as an oracle. And that's why it's called black box. So we're only going to use the circuit to evaluate the underlying polynomial. Okay.
Computational model is counting field operation. It will be reasonable only for the black box model.
Why?
It's non-commutative identity testing. You have to do manipulation. You're not testing. You just break you get an input signal.
Sorry for yeah. So when I say field operations, I'm not necessarily just talking about the black box model. I mean, you could do things like you take a circuit, right, and you look at field elements and you say, aha, there's 5, and like I really like 5. That means the circuit's not 0, right? Yeah. It's like you have like special field registers where you're allowed to store field elements and so on. Yeah. Okay. Okay. So that's the black box model, and now there's also a white box model. And what is a white box model? Not black box. So basically, this is just not this. You're allowed to do whatever you want, and that's because white is the opposite of black, or so I'm told. Okay. So the black box model is, in some sense, it's a more restrictive model. So if you get algorithms in that model, it's a stronger result. Okay. But I want to talk about, we have this efficient randomized algorithm, and we're looking for deterministic algorithms. And it turns out that when you have deterministic black box algorithms, there's a much more convenient object called a hitting set, which Amir defined this morning, and I'm going to define again. Okay, so suppose that you have curly h. It's going to be a subset of your field, right? We have n-variate polynomials, so this is inputs to this polynomial. We're going to call this a hitting set for a class C of polynomials. So some word on notation. Curly C will be a set of polynomials. This is your polynomial ring in n variables, and I'm saying I'm restricting to degree at most d. Okay, so you have a set of polynomials. H is a hitting set for this. If what? I'm going to say that if for all f, you basically have something like this. You can translate questions about syntactically 0 into questions about functionally 0. In C. Yes? Good. Thanks. Then f is non-zero if and only if f is non-zero when you evaluate it only on your hitting set h. Okay. So that is the definition of a hitting set. Right? And so the corollary here, just to this thing I already wrote, is that there's always hitting set of size d plus 1 to the n for any class of polynomials that you have. Okay? So this is an exponentially large hitting set. But what's interesting about this is that it's explicit, in the sense that I don't really need to do any brute force algorithm to find this thing. I just sort of list it, and it's like you can sort of really write it down. It's very, very large, but it's very, very explicit in some sense. I'm not really going to be explicit about what explicit means, but you can kind of figure it out to some extent. What one cute exercise is that this is actually not optimal. Okay, so you can actually get a hitting set of size n plus g choose d. Okay, and I can reference this later in talk, but this is actually the tight size hitting set if you want to hit all possible polynomials in this set. Okay, but it's a fun exercise. Okay, so this is a hitting set, but how does this actually relate to black box deterministic PIT? And dilemma here is that suppose that you have a time t deterministic black box PIT, so I'm going to abbreviate this as black, BB PIT. This is equivalent to having a size, so for some circuit class C, this is equivalent to having size approximately t hitting sets for C. So what this is saying is that without loss of generality, if you have to consider black box PIT, you really only need to construct explicit hitting sets. So this is an explicit hitting set. Okay, and so what's the sort of the proof of this lemma? Well, there's sort of two directions, right? If you have a hitting set, it's pretty clear how to get a black box PIT. You just evaluate it, your polynomial over all points in your hitting set. If you ever get 0, you say the polynomial is 0. If you never get non-zero, you say the polynomial is 0. Okay, so that's pretty easy. What about the other direction? It seems a little bit maybe less obvious. So basically, I'll just leave it as an exercise. Roughly speaking, the point is that when you have a black box algorithm, it's conceivable that you could pick your points adaptively. Like you query your polynomial, and then you query something else depending on your previous queries. And so this is really a question about non-adaptive versus adaptive algorithms. But the point is that adaptivity doesn't help you in any way here. So okay, you see it, but. Right. Yeah, if you keep on getting zeros, there's just no way you can use that information in an adaptive way. And so Natty also sees it. Great. Okay. Cool. Okay, so there's a really, really large hitting set, which is not really useful algorithmically. Are there better hitting sets? Right. So Amir mentioned this morning, which is lemma says, suppose that C is the set of size S circuits. Right, so this is general circuits. Again, it's going to be n varied degree at most d. Then there's a hitting set. So there exists an H, which is a hitting set for C. And how large is it going to be? Well, the size of H is going to be something like polynomial in S, N, and D. Right, so S is the size of the circuits, N is n variables in degree d. Now the challenge here is that this is saying there exists one. It's somewhere out there in the woods all alone. Right? We don't know where it is. Okay. And so the challenge is to basically match this with some sort of construction. Okay. But how do we actually prove that something exists? This is basically by a counting bound, similar to what Amir did this morning. Okay. So the subtlety in proving this, though, is there's a question of what do you do on infinite fields? Because as Amir said, counting over infinite fields doesn't really make sense in some way. You have to do sort of dimension arguments. I don't get paid enough to do dimension arguments, so I'm going to only do counting over finite fields. Okay, so let's do this for FQ. Okay, and I'm going to assume here that yeah, so this is only true. This is going to be in a situation where your field is sufficiently larger than the degree, right? This is sort of what I mentioned already, that you need a large field to make all of this work. Okay, so let's do a proof when Q, say, is at least, I don't know, d squared. Okay. So suppose that you take, again, we're going to make a probabilistic statement. Suppose you take a random hitting set. Okay. So you can take a random hitting set, and they're going to be, just n tuples of points. And if suppose that you have f is a non-zero polynomial, what's the probability that for a non-zero polynomial it's 0 on all the points in H, right? Well, this is basically just a repetition of the Schwartz-Zippel over many, many points, right? So this should be at most d over the size of, you're choosing from FQ, so the size of your set is Q, should be d over Q to the t, which will be at most 1 over square root Q to the t based on the fact that Q is much, much larger than d squared, or larger than d squared. Okay. And then, so this is saying for any individual polynomial, if you pick a random set, it'll hit it with very high probability. Now we want to do a union bound, but we need to say how many circuits are there of a certain size. Right? So you could use arguments like the universal circuit. I'm going to say something slightly different. How many circuits of the size S? Well, recall a circuit is a directed acyclic graph. Right? And I want to say that the graph structure itself is very combinatorial. Right? It's sort of how do you wire edges. But once you fix the edges, you only need to fill in the field constants. Okay? So there's really two parts to this computation. First, there's an exponential in S factor, where it's just 2 to the poly S, and this is the combinatorial part. This is saying, you know, how many directed acyclic graphs are there that you could possibly choose from. Okay? But then you need to fill in all your field constants, and how many possible field constants are there? There's something like Q to the S. Right? Because you have a size S circuit, how many possible times could you use a constant? It's at most S. Okay? So there's the combinatorial part, 2 to the poly S. There's the algebraic part, which is just Q to the S. And we kind of separated the two. Not that you really need to, but. And now we just want to do a union bound, right? So the probability that there exists a circuit of size S, like a circuit, you know, computing some polynomial f, where f on h is 0, well, it's basically going to be 1 over square root t, q to the t times 2 to the poly s q to the s, right? This is just a union bound. And if this is less than 1, then that's saying there must exist some set, which is a good hitting set. So basically, we just need this to be less than 1, and this is true if t is like poly s. Okay. And basically, the reason we chose q to be, say, d squared is because this probability is sort of nicely depending on q. And so this hitting set has no dependence on q in terms of its size. Okay, so that sort of intuitively says that, you know, as even for infinite, you know, if you let this statement go to infinity, this t is independent of q. So intuitively, for infinite fields, you don't expect a dependence. Okay, which is why I did that. Okay, so what did we see? Right, I defined PIT for you. I gave this Schwartz-Zippel algorithm, right? There's a very, you know, wasteful and inefficient deterministic algorithm. Using Schwartz-Zippel, we get an efficient randomized algorithm. We can define hitting sets, say that, you know, there exist hitting sets that are small, but this basically raises this question, like, you know, there's good randomized, very poor deterministic. You know, can we get, you know, efficient deterministic, you know, PIT, whether it's white box or black box, for interesting classes C. Okay, so there's some reason, as sort of discussed, that it seems hard to get efficient deterministic algorithms for general circuits, but maybe for restricted circuits like multilinear formulas or depth repowering, it seems more reasonable. Okay. Okay, so this is sort of the main question of this area. So I gave one question. Does anyone have other questions for me? Yeah, so this will hold over any field. I sketched an argument where, you know, over finite fields, and where the hitting set does not depend on the field size. So intuitively, if you let q in infinity, it should work. But, you know, that's obviously very not rigorous. You need some very basic ideas of algebraic geometry to make that work in general. Okay. So I defined hitting sets for you, but unfortunately, hitting sets are not so cool. So I wanted to find something else. Okay, I wanted to find a generator. And the reason I wanted to find a generator is the following question. So suppose you have a hitting set H for C. Okay. The question is H a hitting set for C times C? So what is this? This is the set of all polynomials f times g, where f is in C and g is in C. And you can say, well, why am I considering this class? Well, the intuition is that what is a hitting set supposed to do? It's supposed to reveal to us whether a polynomial is non-zero. And the fundamental fact about things is you take two non-zero things, you multiply them, they should be non-zero. So intuitively, you should be able to say that hitting sets preserve non-zeroness, so they should also preserve non-zeroness under multiplication. So this seems like, oh yeah, this should really work. And obviously it doesn't, because otherwise I wouldn't ask the question. But you can consider H as a simple example, consider H as 0, 1, and consider C is just x and x minus 1. Okay, so you can see that h will hit everything in C. So that's sort of stupid, but if you have, x times x minus 1 is in C times C, right? And this vanishes on both of these points. Okay, so it's sort of a trivial thing, and we need to fix this in some way. Okay, and it's important for various technical reasons, but it's conceptually, I think, nice. Okay, so what's the replace object that we're going to have here? We're going to have something called a generator. So this is going to be a map from f to the L to f to the n. And because it has many outputs, I'm going to put a bar here. And this is going to be a so-called polynomial map. So what do I mean by a polynomial map? Basically, G is a tuple of polynomials. Okay, so there's going to be a G1 of y, dot, 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 Gn of y. And this is, each of these is a polynomial, so this is a polynomial, each of them is a polynomial in y, and there's n of them, so it's an n tuple. Okay, so this is a polynomial map. And I'm going to say this is a generator for C if what? Well, it's the same thing as a hitting set. It's preserving non-zeroness by converting syntactic questions into functional questions in some way, in the following sense. So for every f in C, we have that f is a non-zero polynomial if and only if f, when you evaluate it on the output of the generator, is also non-zero. So this is slightly different. This is not a functional question. You're just composing it with another set of polynomials. Okay. Right. And so this object is nice because it has a very nice analog with, say, pseudorandom generators for Boolean computation. Right. L is going to be so-called seed length here. And what we're really looking is we want L to be very, very small. It's very clear to get L as n because then you just have the identity map, and then this is sort of clearly works. The challenge is to get L to be very, very, very small. Okay. But let's see immediately how does this solve our question. Right. Basically, the lemma is that if G is a generator for C, then it's also a generator for C times C. Okay. This basically follows the intuition I gave you, which is that G preserves non-zeroness with respect to C. When you have two non-zero polynomials, their multiplication is also non-zero, so it should also preserve non-zeroness for the product. Okay, so it's saying that generators can do something that hitting sets seemingly cannot. So this makes it sort of a more robust notion. But of course, ultimate punchline is that generators and hitting sets are the same, right? Up to some amount of loss, and let me just tell you about that now. Okay, so here's the lemma. Suppose that you have a G, right? This is our generator here. This is a generator for C. What I want to do is I want to extract a hitting set from that, and so let's see how the parameters compare. Okay, I want to say that this implies that if you take G and you evaluate it on some set, so I'm going to pick S, again, as a subset of our field. Right? I want to say G evaluated on this cube is a hitting set for C. But the question is, how big does S need to be? We just need that S is at least to the degree of our polynomial map times D, which is the degree polynomial for our parameters, degree parameter for our polynomials. Okay, so G, right, it's a vector of polynomials. The degree of this vector is just the maximum degree of any polynomial that appears. And yeah, so basically you choose some set, you get the cube, you evaluate the generator, this is a hitting set. Okay, so what's basically the proof of this? It's very simple, right? If f is non-zero, right, that implies that f on your generator is non-zero. Okay, and now we want to find an evaluation of f that's non-zero. That's our hitting set, right? But the point is, what are the parameters of this polynomial when we view it in terms of y? Right, well, g is of degree g, f is of degree f, which is at most d, and so the composition is at most degree of g times d. Right, y has L variables, and so you basically just now plug in the brute force hitting set. Replace y with this cube, and basically this lemma that I proved over here says that it works. Okay, so what basically you're doing here is by using a generator, you're going from n variables down to L, and then you get a hitting set, you just replace it with the brute force thing. So even the brute force thing seems very stupid, if the number of variables you have is very, very small, that's great. Okay, and in the particular regime that's interesting here is you typically want something like L to be constant, and you want the degree of the generator to be polynomial with the relevant parameters. Okay, so this is a little bit different from Boolean complexity, where you're looking for a seed length with is logarithmic. Here you want seed length which is constant, because what is the size of this? Right, the size of this cube is going to be this thing to the L, right? So it's going to be degree of g times d to the L. Okay, so for this to be polynomial, you really want L to be constant, because d is going to be something, polynomial, and g here is going to be polynomial. So you really want a constant variable generator with polynomial degree, and that would give you a polynomial size hitting set. Okay, and then so that's saying that if you have a generator, then you have a hitting set. What about the other way? Well, the lemma here now is basically that the converse also holds. Okay, so suppose that you have H, which is a hitting set for C. What do we want? We want a generator. This gives us a G, which is going to take a single variable, f to the n. Okay, so we had a hitting set. We're going to get a generator where the number of input variables is 1. Well, what are the other parameters that the hitting set could possibly have? It's only, or the generator. The generator has this degree parameter, right? And the degree of G will be the size of H. Okay, so if you have a small hitting set, then you're going to get a generator of polynomial degree. So this basically says that, just before I even prove it, is that the generators and hitting sets are basically the same thing, except generators have this additional robustness thing, but it's sort of a circle, and you can kind of run around in circles, and sometimes that's productive. Most of the time that's not, but okay. Okay, so what's the proof of this? Basically, we're going to, in sort of high-level language, we're going to pass a curve through H. Okay, so H is a sequence of tuples, and I'm not going to do the details because time constraints. But basically, what you want to do is you want to have a generator whose image contains H. So we want that the image of G, so G has one parameter, right? As you range over all of the elements in the field, you want the image of your generator to contain H. And if this is true, then G is a generator. But the question is how, what's the degree parameter? And it's basically going to be H, because you need to do H things of interpolation. Okay. So we have hitting sets and generators, and it's kind of giving us a framework to discuss, actual results now. And so now I want to talk about so-called hardness versus randomness, which is a long-standing paradigm in Boolean complexity for saying if you have some function or polynomial or whatever which is really hard to compute, then in a certain sense this object should look random, because if it didn't look random, then you could somehow do some non-trivial computation on it. And the intuition there is that by having something that looks random but isn't, you can then de-randomize algorithms. In polynomial identity testing, it's all about obtaining deterministic algorithms. So that's basically saying that if you have something hard, you get something that looks random but isn't. So you should be able to de-randomize your algorithms. Okay. So to summarize that, as a high-level picture, so this is about hardness versus randomness, it's the following circle of life, or circle of my life, I guess. Okay, so there's 3 corners here. I shouldn't try this yet. There's lower bounds, right? This is the thing that was talked about this morning. Can you find an explicit polynomial, which is hard to compute? There's the problem of black box PIT, which is can you find a small explicit hitting set for your algebraic computation? There's white box PIT, which is any deterministic PIT algorithm. So these are 3 problems. Okay. Let's draw some arrows in terms of how do these relate. Well, it's kind of clear that if you get black box, then clearly you get white box. Okay, that's a free arrow. It's not too hard. Okay. What it turns out is that typically the way things go is for any motion of circuit class you have, like multilinear formulas or depth repowering or whatever, you first need to get lower bounds. Okay, that's sort of the starting point. Okay, and then you stare these lower bounds until your eyes bleed, and then you hopefully get a white box algorithm. Okay, so this is some hard work. Okay, and then you do some more, and this is harder work. hopefully then you can say, let's look at our white box algorithm and actually distill it and get something black box. Okay, so it seems like you go around the circle and you do a lot of hard work and you maybe get what you want. Okay, but I want to say that this really is a circle because right now it's just like a funky looking diagram. That there is actually other arrows here. Okay, so one arrow is I want to say that if you have black box, you also get lower bounds basically for free. So this is sort of a circle of life. But unfortunately, like this is really this is the hard direction. One question is is there an easy direction? It's not quite as clean, but so I want to tell you about this, so I'm going to do this. I also want to tell you about this arrow. This will be today-ish, 10 minutes from now. But this will only work for general circuits. So it's saying that if you have lower bounds for general circuits, then you can get efficient polynomial identity testing deterministically with black box algorithms. Okay? And then there's another arrow, which is also something like here, which is a little bit more murky to explain, which says that even if you get white box algorithms, you get lower bounds. Okay, so there are really like a lot of arrows here going in both directions. Let's start off with talking about how black box implies lower bounds. Okay, so that's not going to work. Okay. All right, so the lemma here is due to Heinz, Schnorr, and Agrawal. It says, suppose that you have a hitting set. I want to get a hard polynomial out of it. Okay, so suppose that you have H is a hitting set for C. Now, I gave you some trivial constructions, right? There are hitting sets of this size. Okay, I want to say if you can beat this trivial bound by 1, just by 1, then you can do something super amazing. Okay, so suppose that your hitting set here is less than n plus d choose d. Okay, what does that imply? You can get a polynomial in the size of H explicit polynomial f, where what do we have about f is that f, it's a low degree polynomial, n variate degree at most d, but it's outside your circuit class C. Okay, so this is not really a necessarily familiar way to write a lower bound, but basically suppose you have C as the size of a set of size S circuits. Right? Finding a polynomial outside the set of size S circuits is a lower bound. Okay, so this is saying if you get any non-trivial hitting set, you get something which is lower bound. But I want to highlight this in terms of explicitness. What does this mean? It means you can compute f polynomial in the size of h. H might be really, really large, right? All we're pretending is that it's less than this trivial bound, right? So this is not maybe what you'd want. An open question is, can you get f in V and P? Right? If you have a hitting set for, say, size S circuits, does that imply that there's a hard polynomial in V and P? It's not clear. Okay. Okay, but how do we prove this? Well, it's sort of the standard idea here. So proof. Okay, pick f. First of all, we want f to be non-zero, because certainly the zero polynomial is pretty easy. What we want is that f is non-zero, but yet it's 0 on all points in your hitting set. Okay, it's not clear maybe at the moment that such a f exists, or how do we even find it. But let's say, suppose we had this property. I want to say that it automatically means that you're outside C, because by definition, if H is a hitting set, if f is non-zero, it must be non-zero on H. Okay, so this clearly says that this means that f is not in C. But how do we actually find this efficiently, and how do we prove that it exists? Yes. Okay. Well, let's consider the map that takes f and maps it to f restricted to H. Okay. This is a bunch of polynomials, right? This is going to take our polynomial ring, and it's going to map us to a bunch of tuples, a bunch of evaluation points. Okay. And the point is that both of these are vector spaces, and I want to say this is a linear map, which is not too hard to see. Okay, right? So this is a linear map, and what do we want? We want, an f. Let's call this map phi. We want an f which is non-zero, but phi of f is 0. Right? So we want something non-zero in the kernel of this linear map. Right? And we can use linear algebra to do this, right? Because phi, well, sort of the number of variables, right, is basically, this is a map on the space of n varied degree at most d polynomials. Right? How many degrees of freedom are there here? What's the dimension of this space, or the number of variables in this linear system of homogeneous equations, is equal to n plus d, choose d. Right? What is the constraints saying that the image is 0? Right? The constraints, well, the number here is just the size of your hitting set. Right? 1 for each point saying that that evaluation is 0. Right? So if the number of variables is bigger than the number of constraints, there exists a non-trivial solution to this linear system of equations. So basically, that says that we can use linear algebra to find f. Okay. And basically, that gives us this runtime. Okay. Okay. So that's saying that if you have a hitting set, then you get a hard polynomial. Yeah, so it seems like it would also be polynomial in here, but you can do a trick which I forgot. Yeah. Right. Yeah, that's right. Yeah. No, but you need to constrain the coefficients of the polynomial also, right? Because in general, this is the number of variables in your linear system, but you need to say we're only going to look at h plus 1 non-zero coefficients. Yeah. And then you get something which is polynomial only in h and not actually the size of this thing. That's right. Okay, so I only have like 5 minutes, and I have like 10 more minutes of material. Let me just state some stuff. Okay, so there's this theorem of covenants and Pareto, which is going. So I did, from black box PAT to lower bounds. I want to kind of sketch the other direction. Okay, and so this is a bit more harder to state. But suppose that you have p, which is an L variable. Let's say it's multilinear, because we can. It's L variable and multilinear, and it's hard. Okay, how hard is it? It requires 2 to the omega L size circuits. So this is basically about as hard as you could possibly want. And this will imply that for size S circuits, they have a polynomial to the log S size hitting set. Okay, so this is a quasi-polynomial size hitting. It's not quite polynomial, but it's basically saying if you get something which is a maximally hard polynomial, you basically almost get optimal size hitting sets which are explicit. Okay, and so this is giving you basically going from lower bounds to black box PIT. The challenge, the problem with this, it doesn't work if you say we get lower bounds for multilinear formulas or we get lower bounds for depth repowering or whatever. It only seems to work in most of the time is if you get lower bounds for general circuits. Otherwise, it put me out of a job or something. But basically, you really need really strong lower bounds to get this thing. So unfortunately, we cannot run this arrow to get black box PIT for most classes. You really have to go the hard route. It's unfortunate. Okay. So what's the basic proof? Well, there are a couple ideas here. So as I said, we really just need a generator, right? We need a map G, which takes L variables to N, where L is very small. So we're going to take L to be like log or something eventually. But let's just do something very simple, which is let's get a G, which goes from F to the L plus 1. Okay, it's like the first step. This is the first step. That's step 1. Step 2 is to say there are 2 problems. And step 3 is to fix them. Okay. And so the thing I'm going to do is I'm just going to state step 1 and then wave my hands on how you can fix problems I'm not going to define. Okay, so the intuition for step 1 is basically coming from this hardness versus randomness thing, which is saying that if you have some polynomial which is really hard, then it should look really random. Okay, so that very much inspires the generator, which is as follows. So consider the map X, Y. Your input is Y, and your output is Y with P of Y. Right, so P is our hard polynomial. We're just depending it here. Right, so this is L to L plus 1. We want to say that this should look random. Right, and why should this look random? Well, suppose that F of Y, P of Y, is 0. Right, despite the fact that F, Y, comma, Z is non-zero. Right, this would mean that this map had failed to be a generator. It's a non-zero polynomial, it's 0 in the generator. This implies that Z minus P of Y divides F of Y, comma, Z. Okay, this is a basic Gauss's lemma or something. Okay, And there's this theorem of Kaltofen, which says that this implication implies that the size of P, the circuit size of P, is at most the size of F. Okay, but the point is that F is supposed to be a small circuit, right? Those are the ones that we care about hitting, and P is one which is large, right? So this requires large circuits, and this is supposed to be small, right? So this is a contradiction to this statement. Okay, so this is saying this is a generator if P is hard enough. Okay, and then to complete this, what you need to do is you need to evaluate this on evaluate P on many disjoint subsets of input. So what your generator is going to end up looking like, something like this. So here you're going to have Y. You're going to pick some subset S of your inputs. And what's going to happen here is this is going to be P on Y restricted to this subset. Okay, you're going to pick a bunch of different subsets and evaluate P on these, and you're going to get an exponentially many number of outputs this way, because you choose your set family to have many, many sets. And then you do some sort of magic, and you basically use this sort of argument again to say that if there was a small circuit which vanished on here, that would contradict the fact that P requires large circuits. But there's some details there, and I think I'll stop, and I think we come back 10 after. Okay, great.